We have seen in the previous video the procedure for determining whether two sample means could have been taken from the same population. This was done using the z-test for two sample means. In this video, we will first see the t-test for two means and then the t-test for two dependent sample means. The t-test for two sample means is based on exactly the same theory than the z-test for two sample means. Two of the conditions for using the z-test was that our sample n's were higher than 30 and that we know the population standard deviations. It happens, though, and rather frequently, that at least one of these conditions are not met. In this situation, we will turn towards the t-test for two sample means. Again, we'll do a full example going through the 7 steps. We will ask ourselves the question, are the ages of Bishop's University students from outside of Quebec significantly different from the age of students from Quebec? You might notice that the values that we have to do this test are not exactly the same as the ones we had in the previous video. First, we must choose our test. We still have two variables, with the independent one being provenance with two qualitative values, and the dependent quantitative variable being age. Both samples are random samples, and both of our samples have n's that are bigger than 30, but we are lacking one of the population standard deviations. As such, we must revert to the t-test. Our question asked if the ages of both samples are significantly different. There is no sense of direction here, so we have a two-tailed test. Our null hypothesis will be that both mean ages are equal, and our alternative hypothesis will be that both mean ages are not equal. We will again use a level of significance of 0.05 because nothing else was specified. When choosing our critical value, we must verify if the sample sizes are the same. If not, the degree of freedom for the samples will be different. In our example, our sample n's are actually different, so we choose the degree of freedom that is the lowest in order to select our critical value. The lowest would be 34, so in our table, the degree of freedom of 34 does not appear. We will simply choose the closest value, which is 35. As such, our critical values will be of plus or less 2.03. The equation for calculating our value is almost the same as previously, with the notable exception of replacing the population standard deviations with the sample standard deviation. When we plug in the correct numbers in the equation, we end up with a calculated value of minus 3.27. Because our calculated value falls in the rejection area, we must reject our null hypothesis. Our final statement will actually be the mean age of Bishop students from outside of Quebec is significantly different than the mean age of Bishop students from Quebec. We can say that there are two age populations for Bishop students. In the example we have used, both samples are said to be independent from each other. In other words, the objects in the samples were not related one to another or not paired. When it is the opposite, samples are said to be dependent. For example, if a researcher does a before and after test for a diet on the same people, then the samples are dependent. Another example would be if you had two groups that were separated based on pairs. Consider this case. A researcher wants to check the efficiency of two study methods. He will pair up students with identical IQs and then split all the pairs into two groups to ensure both groups have similar IQ distributions. Although other factors can influence the results, IQ is not one of them because they are the same in each group. Now let's do a full example for t-test for two dependent sample means. A track and field official decides to test the performance-enhancing properties of a well-known energy drink and wants to check if it significantly increases performance. During a practice, he makes athletes do 3 long jumps and compiles the mean. During another practice, he makes the same athletes drink a full can of said energy drink and makes them do 3 long jumps, and again he compiles the means. Here are the results of his tests in meters. First, again, you must choose the test. We have a qualitative independent variable with 2 values and a quantitative dependent variable. But because both sets of measures were done on the same individuals, our samples are said to be dependent. Now we must do the t-test for dependent samples. Note that there is no z-test for dependent samples, so as soon as your samples are dependent, you must continue with the t-test for dependent samples. We are asking if performances will be significantly better, so this is a right-tailed test with these statistical hypotheses. You could have a left-tailed test or a two-tailed test for dependent samples. No surprise here, our level of significance will be 0.05. And step 4 is to find the critical value. Our degree of freedom is 8, giving us a critical value of 1.86. Here's where things shake up a bit. To calculate the test statistic, we must use this equation, where we have t is equal to the mean of differences, which will be divided by the standard deviation of differences, which is divided by the square root of n. To calculate the mean of differences, first you must find all of the differences between the two samples. So here in the table you have all of the differences where we did the sample without minus the value in the sample with the energy drink. You sum all of those differences together, which gives you minus 0.1 and divided by n, just like you would do for a mean. So your mean of differences is minus 0.01. For the standard deviation of differences, feel free to use the first equation I showed you on standard deviation, but you can also use this one. Now it looks a bit more complicated, but we'll break it down. First, you notice we have a lot of n's in there, so we can replace the n's by 9, which is our actual n value. It gives us this new equation. Now here we have to pay attention to where the parentheses are. In one case, we have to add up d and then square that result. And then what we have to do for this one here is to square all of the d's and then add all together the squares of d's. Now in this table I have given you the sum of d and the sum of d squared. So if we add these values correctly into the equation, this is what we get. Calculated it all together, this is further what we get for a standard deviation of differences of 0.17. Now we have all the values we need to calculate the test statistic. So we have minus 0.01 divided by 0.17, which is divided by the square root of 9. So our t, calculated t, is minus 0.18. For a statistical decision, we compare minus 0.18 or calculated t to 1.86. Calculated t is definitely not in the rejection zone, so we do not reject the null hypothesis. So to resume the situation, our final step, we can say that the consumption of an energy drink does not positively affect long jumping performances. Now it's your turn. Pause the video and answer this question. At a 0.01 significance level, is there a significant difference in temperatures between the two given years for these 10 Canadian cities? With a calculated value of 1.25, there is no significant difference.